Welcome back everyone. So in this last video of the mole topic, I will be talking about dot points 8.6 to 8.8, which involve empirical and molecular formulas as well as percentage compositions. So we're just going to start with empirical and molecular formulas. The main reasons why we're going to bring this up is because you can use percentage composition as the way to determine the empirical formulas of newly synthesized compounds. So this is one application of percentage compositions and the mole concept, which I will explain in a little bit. So first of all, let's look at the definition. Molecular formula, you've seen this before, hopefully, is the actual number and type of atoms present in a molecule. So you have definitely seen molecular formulas. Pretty much all the formulas that you have seen before are molecular formulas. So for example, H2O, this is a molecular formula. It tells you that a molecule of water has 2 hydrogen atoms and 1 oxygen atom. You can also have something really big such as C6H12O6. This is glucose. Or maybe we can have C2H4O2. So a lot of these examples, well, the last two anyway, are organic molecules. And the interesting thing about organic molecules is that you can have multiple different combinations of atoms from the same types of element, in this case, carbon, hydrogen, and oxygen. You can also have things like C3H6, for example. This is propene. Now, empirical formula is a formula that shows the simplest whole number ratio of the elements in a compound. So if the molecular formula is H2O, my empirical formula in this case is also H2O, because a 2-to-1 ratio between hydrogen and oxygen is already the smallest whole number ratio. So the empirical is just H2O here. But if you have something like C6H12O6, this is not the smallest or simplest whole number ratio. I can divide every number by 6 and I will get something that is CH2O. So this is the simplest whole number ratio, which is really a 1 to 2 to 1 ratio between carbon, hydrogen, and oxygen. The next example, which is C2H4O2, I could also simplify this ratio further by dividing every number by 2, and I would get CH2O. So you can see here that you can have two different molecular formulas that have the same empirical formulas, because empirical formulas just tell you the ratio between the number of atoms of each element. It doesn't indicate exactly how many atoms of each element you actually have. So this is the same empirical formula, even though it has a different molecular formula. And then you have something like C3H6. I can simplify it by dividing both numbers by 3, and I would get CH2 as the empirical formula. So empirical formula can be the same as molecular formula as in the first example, or they can be different, and you can have one empirical formula being giving rise to multiple molecular formulas. So I think that's the 2 points that I just made. So molecular formula can be the same or different from its empirical formula, and different molecules with different molecular formulas can have the same empirical formula. All right, so the first thing that we need to do in terms of skills is to be able to determine molecular formulas from empirical formulas and molecular formula mass. So basically what you just need to do is you just need to find a ratio, a mass ratio between them. So I'm going to go through this example. So example 1, given that the empirical formula of hydrocarbon is CH, so the first piece of information that you have is the empirical formula. And the empirical formula in this case is CH. Okay. And then you also given the molar mass. Now, if the question say, given the empirical formula of hydrocarbon is CH and its molar mass is 26, it is actually referring to the mass of the molecule, not the empirical formula of mass. So this is the molar mass has the same number as the molecular formula mass, which is 26 in this case. And the question asks you to find the actual molecular formula. So if you're given the empirical formula and the molecular formula mass, and you need to find the molecular formula, there's only one extra piece of information that you need to find, and that is the empirical formula mass. And you can work this out using the periodic tables and the empirical formula that's already given to you. So the empirical formula is CH, which means that the empirical formula mass, which is going to be the same as the molar mass of CH, this is going to be 12, which is the molar mass of carbon. Let me just write that. So mass of carbon plus mass of hydrogen. So there is one carbon and one hydrogen atom in this empirical formula. And if you look at the periodic table, the mass of carbon is 12 and the mass of hydrogen is 1. So the empirical formula mass in this case is 13. So the difference between the empirical formula and the molecular formula can be found by comparing the masses of them. So there is a ratio of 2 to 1, or if you just go 26 over 13, that's 2, which means that the molecular formula mass is going to be twice the empirical formula mass, which means that in order to achieve a mass of 26 and still having the same ratio at the empirical formula, I would need to double the amount of carbon and hydrogen to go from empirical to molecular formula. So the molecular formula in this case is going to be C2H2. So it's twice the amount of carbon and hydrogen. So it still has the same 1-to-1 ratio between carbon and hydrogen, but it now has a mass of 26. Okay, so that's the first thing, determining molecular formula from empirical formula and molecular formula mass. The second thing that we're going to look at is percentage composition. Specifically, it is percentage or proportion by mass. So we're looking at mass composition here of different elements in a compound. And this is the formula if you haven't heard of the concept of percentage mass composition before. Basically, you need to find the mass of the element in the compound over the mass of the compound and multiply that by 100. So let's go through a few examples. This is the first one. So the question asks you to determine the percentage composition of hydrogen in H2O. So this is the formula, and I'm just going to use it. So I need to find the mass of hydrogen in H2O. And so because I'm given the formula of H2O here, I'm going to compare the mass of hydrogen in 1 mole of H2O, if you will, over the molar mass of H2O, which is the mass of 1 mole of H2O, so over m of H2O. And if you look at the formula of H2O, there are 2 hydrogen atoms and 1 oxygen atom. So the mass of hydrogen in H2O will be 2 times the molar mass of H over the molar mass of H2O, and you do need to multiply this by 100 to get a percentage. So if you look at the periodic table, you can work out that the molar mass of hydrogen is 1. So it's just 2 times 1, which is 2. And the molar mass of H2O, maybe we can find it down here. Molar mass of H2O is 2 times the molar mass of hydrogen plus 1 times the molar mass of oxygen. So that should equal to 18 grams per mole. So it's basically 2 over 18 times 100. So 2 over 18 times 100. So I go with 11.11% or something like that. Okay, so that's example 2. We're going to do another example here. So this is a little bit different because if you read the question, so you have 1.308 gram sample. So the mass of the sample is 1.308 grams, and it contains potassium, chromium, and oxygen. And they tell you that the mass of potassium is 0.348 grams. The mass of oxygen is 0.498 grams, and you are required to determine the percentage compositions of all 3 elements. So we're going to use this formula again, and you can see here that the mass of chromium is missing. There are 2 ways that you can go about solving this problem. You can either find the mass of chromium, which is just the total mass of the sample subtracting the mass of potassium and oxygen, because there are only 3 elements present in this compound. So I can go with 1.308 minus 0.348, and then minus 0.498. So I could do that. I ran out of space over there. So, or you can find the percentage composition of potassium and oxygen and subtract that from 100, because once again there are only 3 elements present, so the sum of all the percentage compositions should add up to 100. So I think I'm going to go with the second method. So I'm just going to start by finding the percentage composition of potassium, which is mass of potassium, so 0.348 over the mass of the sample. So the difference between this question and the previous one is that this one doesn't give you the formula of the substances of the compound, but it gives you the masses of a sample of the compound as well as the mass of each element. So times 100, so this is going to be 0.348 divided by 1.308, and so I have 26 point, let's go with 3 significant figure, 6%, and percentage by mass, percentage composition of oxygen is going to be 0.498 over 1.308 times 100. So this one is 38.1%. And then the last thing is I'm going to find the percentage composition of chromium, which is just 100 minus 26.6 minus 38.1. Okay, so 100 minus this, and then minus 26.6, so it's 35.3% for chromium. So box your final answer. So that's the first one, and the second one, and the third one. Okay, so that's example 3. The last thing that we need to talk about is how do we connect percentage compositions and empirical formulas, and then eventually molecular formula, which normally is the reason why we do all of this, is we want to know the formula of something, for example, you just discovered or you just produced. So these are the steps that you can follow for finding empirical formula given percentage composition. And they either give you percentage composition or the mass of the element in a sample of the compound. So 5 steps, write the element present in the compound, write its percentage composition or mass proportion or mass, and then we're going to convert the mass to the number of mole by dividing each percentage of mass by the molar mass of the relevant element, and then divide each ratio by the smallest quotient or the smallest mole. And then from there you need to express the ratio as whole number ratio. So I'm just going to show you 3 examples of how to follow these steps. You may want to refer back, but I'm going to try to do the color coding though. All right, let's start with example 4. So if we read the question, we know you have 9 grams of a compound and it contains only carbon, hydrogen, and oxygen, and it's about to contain 4.8 grams of oxygen and 3.6 grams of carbon. You need to calculate the empirical formula. So you know that this is a question asking you to find the empirical formula, so you can follow these steps, which are steps for finding empirical formulas. Okay, so step 1 is I'm going to list the elements present in the compound. It contains carbon, hydrogen, and oxygen. So I'm just going to do 3 columns. Carbon, hydrogen, and oxygen. So that's step 1. So I basically looked at this part of the question. Step 2 is to write the percentage mass or the actual mass of the compound, sorry, of each element of the compound. So I know that you have 9 grams of the compound here and it has 4.8 grams of oxygen. So I'm just going to write, normally what I tend to do is I put a little, so m in grams, so I know that this row is for mass. So for oxygen is 4.8 and for carbon is 3.6. So you can see here that the actual mass of hydrogen is missing, but you should be able to work it out because the mass of everything is 9 grams. So the mass of hydrogen is going to be 9 minus 4.8 minus 3.6. Okay, so 9 minus 4.8 minus 3.6, which is 0.6 grams. So the mass of hydrogen is going to be 0.6. Okay, The next thing that you need to do is to determine the number of mole of each element based on the mass. So you're going to find the number of mole here, and you're going to use the triangle that relates mass with number of mole if you really like triangle. And basically we already have mass and we need to find the number of mole, and you can obtain the molar masses of these elements from the periodic table. So the first one is going to be mass of carbon divided by the molar mass of carbon, which is 12. For the second one is 0.6 divided by 1, which is the molar mass of hydrogen, and 4.8 divided by 16, which is the molar mass of oxygen. And then that would give you 0.3, 0.6, and 0.3. So these are the number of moles of each element in this compound. Now, the next thing I'm going to do is to divide everything by the smallest mole so that I can get a whole number ratio. So I think I may have to write it down here. I think we don't have enough space. So once again, CHO. And for step 4, we have 0.3 divided by 0.3. So the smallest mole in this case is 0.3. So I'm just going to divide every number by that just to convert this ratio into a whole number ratio. So I will end up with a 1 to 2 to 1 ratio. And remember that once you get to this step, you do have to answer the question by writing out the actual empirical formula. And the actual empirical formula in this case is CH2O. So 1 carbon and 1 oxygen. You don't have to write the subscript if it's 1. So just CH2O. I don't think it's wrong to write C1H2O1, but I think this is the convention. All right, let's go through another example. The difference between this example and the previous one is that it doesn't give you the actual mass of the element, but it gives you the percentage composition. So let's just start by reading the question. A compound of carbon and hydrogen. So I know that it contains carbon and hydrogen, and it is analyzed and found to consist 75% by mass of carbon and 25% by mass for hydrogen, and you need to determine the empirical formula again. So a very quick way to get around the percentage composition is you can just assume that if you have 100 grams of the compound, 75 grams will be carbon and 25 grams will be hydrogen. So I just convert the percentage to a mass simply by dropping the percentage size. So you have 75 grams of this and 25 grams of this. You don't have to go with 75, 25, just needs to follow the same ratio. So it could be 3 grams of carbon to 1 grams of hydrogen and something like that. So this is the mass. I have to go through the step again. So the next thing I'm going to do, this is step 3. That was, okay, that was 2, finding the mass, and step 1 was to list the element. So step 3 is to convert the mass to the number of mole. And what I'm going to do is just to divide this mass by the molar mass of each element. So in the case of carbon, it will be 75 divided by 12. And for hydrogen is 25 divided by 1. And you're going to get 6.25 for carbon and 25 for hydrogen, and this would be the number of mole of each element. The next thing that I have to do is to divide this by the smallest mole. So the smallest mole in this case is 6.25, which is carbon. So I'm going to divide that by everything by 6.25, and that should give me, let me just rewrite this, 1 to what's 25 divided by 6.25 is a 1 to 4 ratio. And then finally you can write the answer. So the empirical formula, for every 1 carbon you need 4 hydrogen atoms. The empirical formula is going to be CH4. All right, I'm going to go through one more example. This one's very similar to example 4, but there's one exception. This is actually the same example that we did earlier, except that instead of asking for percentage composition, I am asking for empirical formula in this case. So I'm just going to once again start by listing the elements present. So you have potassium, chromium, and oxygen. So K, Cr, and O. And then the next thing I'm going to do is I am going to list the mass of the 3 elements. So I'm trying to find mass in grams here. So for potassium is 0.348 grams. For oxygen is 0.498 grams. And we'll need to find the mass of chromium, but we should be able to because we have the mass of the sample. So 1.308 minus 0.348 0.348 minus 0.498. Okay, so 1.308 take 0.348 take 0.498. Okay, so that's 0.462 grams. And then from here, you should be able to find the number of mole of each element. Okay, so we're gonna go with number of mole. So you need to look up the molar mass of each element from the periodic table. For potassium will be 39, for chromium I think is 52, and oxygen is 16. Let's hope I remember that correctly. So do the math. We're gonna have 0.0089 and then 0.498 divided by 16. This is 0.031 or 348 divided by 39. That's 0.0089 again. So 0.0089 it's going to be the smallest number of mole. And then for step 4, what I'm going to do is I'm going to divide everything by the smallest mole. So this is 0.0089 divided by 0.0089 and then 0089 again. So the first two is going to give you a 1-to-1 ratio. It's really just to see what the oxygen will give you. Okay, I think I need to translate this to here. So we're looking at K, Cr, and O. So it's really just try to keep the exact values as much as possible. So I ended up with a 1-to-1 to 3.5 ratio. Now you actually not finished here because you can't, even though this is a good correct ratio, it's not the smallest whole number ratio because you have a decimal here. So I actually need to multiply this by 2 to get the smallest whole number ratio before I can write the empirical formula. Simply because you don't write oxygen 3.5 in a formula, is always whole number. So the empirical formula is going to be K2Cr2O7 or potassium dichromate. All right. So that is it. There are a few more examples that you can practice and you can check the answers as well. Thank you.